Hey guys, welcome. Yeah, so my video series on trig sub, I have a total of 7 examples with 4 main examples, starting with example 0, explaining why trig sub works. And then after those 4 main examples 0 through 3, we have 2 more challenging examples, one of which is this. The other I put out about a year ago, and it's about finding the area of a generic ellipse centered at the origin with minor axis A and major axis B. I'll try to link that video below this, but you can also just YouTube search it. And of course, to conclude, I'll make one hard example video about like finding the area of a crescent shaped lunar region. I don't know, something like that. So look out for that. Anyway, let's get started with this video here. So how do we do this? Well, first, perhaps this falls in the more challenging category because it's not immediately clear that we should do trig sub. Because usually inside the square root quantity, when we suspect trig sub, we'll have like something plus something or something minus something. It's not like 3 terms. But no problem. What we're going to do to start is just complete the square on the quadratic and the square root in the denominator. And so that we could first use this as a transition, as a rewriting of our original integral, and finish the job of completing the square by writing this, right? Now, all 3 integrals are the same, right? They're equal. But now looking at this last version, so the last rewriting of our original integral, it's pretty clear that the trigonometric substitution here should be like for x plus 1, and we should make x plus 1 2 times sine alpha, beta, theta, no, delta. So yeah, x plus 1 is going to be 2 sine delta. And instead, notice, we could have also made x plus 1 2 cosine delta, just as effective, but we've been using sine instead of cosine, so when we're getting like, you know, a quantity inside the square root that's like something minus something, we've been using sine, so let's continue that trend. But my point is that you could swap the sine here to cosine, and it would work just as well moving forward. All right. Now, where to from here? Well, we need dx, and we get there by taking the derivative of this last equation on both sides. So if x plus 1 is equal to 2 sine delta, then clearly dx will have to be 2 cosine delta d delta, right? All right. And then now we're ready to rewrite our original integral using these trigonometric substitutions, and it's going to look like this. The only thing I need to explain perhaps is this quantity 2 sine delta minus 1 in place of x, and even that doesn't really require a lot of explanation because our substitution to start is x plus 1 is equal to 2 sine delta, so then x will have to be 2 sine delta minus 1, right? Okay, so maybe that's what I needed to explain, but okay, you get it. Now, next, we're going to simplify in the denominator inside the square root and replace 2 sine delta all squared with 4 sine squared delta, right? Doing that, we could write this. And if you've watched the main examples, you know that this is business as usual. And next, we're going to, inside the square root in the denominator, factor out the 4, right? And we do that. And what's that going to do? It's going to do this. And now, clearly, inside of the square root in the denominator, we have 4 times 1 minus sine squared delta, where we know 1 minus sine squared delta is cosine squared delta. So that's our next move. And of course, now, taking out 4 cosine squared delta from the square root in the denominator, we could simply write in the denominator 2 cosine delta, right? Oh, how nice, because from dx, we had a 2 cosine delta. So those guys, which have highlighted in green here, those guys can take care of each other. And when they do, our integral will become very simplified, and it'll look like this, right? All right, now we need some space. So here's that, and pick up where we left off. So that's here. And now what? Now move forward from here and see that, it's pretty easy integration. The integral of 2 sine delta is negative 2 cosine delta, and then the integral of negative 1 is going to be negative delta, since we're integrating with respect to delta, right? And then, of course, plus c. But now we have a little bit of work left to do, because what is cosine delta? What is delta? Well, we're going to start with our original substitution, which is x plus 1 equaling 2 sine delta, and divide on both sides by 2 to see that x plus 1 divided by 2 is sine delta. So then, if that's the case, we see that since we know cosine delta is the square root of 1 minus sine squared delta, and we know that sine delta is x plus 1 over 2, we can replace this sine squared delta with x plus 1 over 2 all squared. Because this here, x plus 1 over 2 all squared, is equivalent to sine squared, and that's what we need, right? Okay, cool. Now, inside the square root here, you can do a little bit more simplifying, but it's just algebra that you should know how to do, so I'm not going to do that. Instead, I'm going to show you that delta will have to be sine inverse of x plus 1 divided by 2, and that's pretty clear. If x plus 1 divided by 2 is equal to sine delta, then delta is sine inverse of x plus 1 divided by 2. All right. So now we've got all the pieces together. We know cosine delta, it's right here, the square root quantity right here. And we've got delta, it's right here, sine inverse of x plus 1 over 2. So our final answer is unsurprisingly going to look like that, right? Okay, cool.